Now back to the fundamental theorem part 1. Recall that it says if f is continuous on the closed interval from a to b, then the function g defined by g of x equals the definite integral from a to x of f of t dt on this closed interval is the antiderivative of f, i.e. g prime of x equals f of x for all x between a and b. Now recall we said that if we assume that the antiderivative of small f exists, then this theorem is quite easy to prove, because then we can use the evaluation theorem as follows. Then the derivative with respect to x of g of x, which is equal to the derivative with respect to x of the definite integral from a to x of f of t dt will equal the derivative with respect to x, and then using the evaluation theorem, the derivative with respect to x of capital F of x minus capital F of a, where capital F is the antiderivative of small f, and applying the derivative into the brackets, we'll get capital F prime of x minus 0, since this is a constant, and since capital F is the antiderivative of small f, capital F prime will equal small f. So here we assumed that the antiderivative of small f exists and it's equal to capital F. We want a proof that does not make this assumption. Now, in order to get an idea of what the proof of the fundamental theorem will be about, let's look at the following illustration. Here we have the graph of y equals f of t. We let the area from a to x under the graph of f of t equal to g of x. Then the green area under the graph will be the area under the graph from a to x plus h minus the area under the graph from a to x. In other words, the green area over here will be g of x plus h minus g of x. So then the green shaded area, which we know comes to g of x plus h minus g of x, is approximately equal to the area of the rectangle with width h and height f of x. We divide by h on the left hand side, so then g of x plus h minus g of x all divided by h will be approximately equal to f of x. So intuitively we know that if we let h approach 0 and take the limit, in other words the limit as h approaches 0 of g of x plus h minus g of x all over h, then this will equal f of x. And on the left hand side we basically have the definition for g prime of x. So this is essentially what we want to show in the proof. We also want to show that this is true not only for functions that are positive, but for any function, whether positive or negative. We want to just briefly look at two of the tools that we will use to prove the fundamental theorem with. The first one is the extreme value theorem from differential calculus. Recall that it says if f is continuous on a closed interval from a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in the closed interval from a to b. The second tool is property 10 of definite integrals. Recalls that it says the following: if f of x is greater than or equal to small m, but less than or equal to capital M. In other words, the function f of x lies between y equals small m and y equals capital M on this closed interval, then the definite integral from a to b of f of x dx is greater than or equal to small m times b minus a, but less than or equal to capital M times b minus a. In other words, the area under the graph will lie between the area of the small rectangle over here, which has length b minus a and width small m, and the area of the large rectangle, which has area b minus a times capital M. So let's look at the proof. Firstly, we let g of x equal the definite integral from a to x of f of t dt, and we let x and x plus h be in the open interval from a to b. Then g of x plus h minus g of x will equal the following. It will be the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. So we get these two integrals simply by substituting in firstly x plus h for x and then x for x. Now we can rewrite the first integral on the right hand side by using property 5 of the definite integral. So we can write it as the definite integral from a to x of f of t dt plus the definite integral from x to x plus h of f of t dt. And then we still have minus the definite integral from a to x of f of t dt. Note that these two integrals cancel, and we are left with the definite integral from x to x plus h of f of t dt. Geometrically, this should make sense. Remember that g of x plus h is the area under the curve from a to x plus h, and g of x is the area under the curve from a to x. So the area from a up to x plus h less the area from a up to x then is the area from x to x plus h under the curve. In other words, this area over here. Our next step now is to divide by h, since h is not 0. So then the resulting equation divided by h will give the following: g of x plus h minus g of x all divided by h will equal 1 over h times the definite integral from x to x plus h of f of t dt. So basically, we're dividing the last equation through by h. And we will call this equation star. Now, let's first assume that h is greater than 0. Since f of t is continuous on the closed interval from x to x plus h, by the extreme value theorem, there exist numbers c and d in this closed interval from x to x plus h such that f of c, which we can call small m, is the absolute minimum on this closed interval. So the absolute minimum of f on the closed interval. And f of d, which we can call capital N, is the absolute maximum of f on the closed interval from x to x plus h. Then, by property 10 of definite integrals, the definite integral from x to x plus h of f of t dt will be greater than or equal to small m times h, but less than or equal to capital M times h. And we know that small m is f of c, and capital M is f of d. We now divide through by h, and we get f of c less than or equal to 1 over h times the definite integral from x to x plus h and this is less than or equal to f of d. Now recall our asterisk equation from earlier, and we've just proved this sandwich inequality. So we can replace the middle part of the sandwich inequality with g of x plus h minus g of x all over h. This inequality can also be proved similarly when h is less than 0. Now we let h approach 0. Now, since c and d both lie in the closed interval from x to x plus h, as h approaches 0, both c and d will also approach x. So then the limit as h approaches 0 of f of c will be the same as the limit as c approaches x of f of c. And since f is continuous at x, this will equal f of x. Similarly, the limit as h approaches 0 of f of d will equal the limit as d approaches x of f of d, and this will equal f of x. Now finally, note that g of x plus h minus g of x all over h is squeezed between f of c and f of d. And we have just shown that the limit as h approaches 0 of f of c equals the limit as h approaches 0 of f of d and is equal to f of x. So then by the squeeze theorem, we can conclude that the limit as h approaches 0 of g of x plus h minus g of x all over h is also equal to f of x. And this is nothing but the definition of the derivative of g. So we have just shown that the derivative with respect to x of the integral from a to x of f of t dt equals f of x. Then lastly, the fundamental theorem of calculus part 2 is just the evaluation theorem which we've already proved earlier.